Hello everyone. So in the following few weeks, we are going to explore a type of function called exponential function. And the exponential function are a function that is based on the concept of repeated multiplication. So for example, let's say you're folding a sheet of paper. So let's say you have a sheet of paper. So if you don't fold it, there's going to be exactly one layer, right? So one layer because you're not folding it. And let's say you fold it once. Then now you're going to have two layers. So let's say you throw it again. So you take that, whatever you have back there, and then you throw it again. Then what does that actually look like in here? Let me see if I can draw it. It will be something like this, right? Something like this. So now you actually have 4 layers of paper. Now I won't be able to draw that anymore, but you know what happened when you take that and then you throw it again is you're gonna get double the paper again, which is gonna be 8 times. So now you started to see a pattern that each one of these is just multiplied by 2. So any extra throw that you do, you're gonna have 2 times more paper, like 2 times more layers, right? So if you take a piece of paper that has 8 layers and then you throw it again, then you're gonna have 16 layers. And then if you throw it in half again, you're gonna have 32 layers. So that makes sense, right? So you keep multiplying by 2, multiplying by 2. So you're multiplying by 2 in each step in this case. So if you want to write down a function that represent, so let's say I want to ask you a bigger number. So let's say, hey, you said start with one piece of paper. So how many layers of paper will you get if you throw it, like, let's say, 20 times, 30 times? Now you could just keep multiplying and get to the answer, but that would take a long time, right? So if we are smarter about this, then we think about the pattern, which is going to be L. So I'm going to use L for layers. So L, which is the number of layers, is equal to, in this case, 2 to the power of n, where n is the number of flows. So in this case, so this is the variable. The variable is actually in the exponent. So the variable is in the exponent, which is something new, right? So we're used to having variables, x to the power of something, but now it's something to the power of x. So the variable is in the exponent. So this number 2 in here is the multiplier. So you could have something that multiply by, 3 times every time. Not in our situation, it's going to be 2. So this is a multiplier, which is what we call the base of the exponent, right? So that's the base. And then, so if you use this equation, let's say we can check it. So for example, if you have one layer, then it's going to be 2 to the power 1, because n is the number of layers, right? So n is the number of flow, where L is the number of layers. So this is layers, and that is the number of flow. So this is actually how many flows you have. So number of flows in here. So if the layer is, so let's say you don't flow at all, which is 0, 2 to the power 0. Anything to the power 0 is 1, and so on, right? If you have 1 in there, then 2 to the power 1 is 2 layers. If you have throw it twice, then 2 to the power 2, which is 4. So we have 4 layers, right? So it's matching the numbers that we have on the left, on the right hand side. So what if we now answer that question, which is what if we throw it 10 times then, right? So if you throw it 10 times, so think about it, what does that mean? 10 throw, which means n equals to 10. So then you have L, which is number layer, is 2 to the power of n, and in this case, it's 2 to the power of 10. So what is 2 to the power of 10? It will actually be 1024 layers. So the number goes up really fast, as you can see. Only 10 throws later, you have thousands of layers, right? Now another one, so how about 12? Well, okay, so what if we throw it by 2 more, right? So n equal to 12 in this case. So n equal to 12. And then we take the number of layers. So layers 2 to the power of n, in this case, is 2 to the power of 12. And then we use a calculator to calculate 2 to the power of 12. And then we get 4,096. So it's just 2 more throws, 4 more times the number of layers. So a lot of layers. So the third thing you should realize with these type of function, which is what we call exponential function, when the variable is in the exponent, the first thing you can observe is this. Exponential function, okay, so exponential function, which is a function that has a variable in the power, so in the exponent. So exponential functions increase very, very quickly. Okay, so it increases very, very quickly. Okay, so you throw it twice, like 2 more times, right, from 10 to 12, and you're getting like 3,000 more layers. So it increases very, very quickly. Okay, so now let's look at some other example. So exponential function usually have the form that we just saw, which is something to the power of x. Now, but it can also have some other numbers in front of it. So in this case, now I'm highlighting, what exponential function could look like. So y equal to a number multiplied by the base to the power of x. So the exponent is on the x. A and b are usually some numbers that you need to determine. Now, but it's not, the exponent is only on the b term though, not on the a. Okay, the exponent is only on the b term. So now in this situation, of course we don't want a to be 0 or b to be 0, because if it's 0 then it's y equals 0. It's just a line, so it's not fun at all, right? But also the base can be negative, so we're gonna have make sure that the base, which is that b, so b can be negative, so it's always a positive number at least. Okay, so of course b also cannot be 1. If b equal to 1, you're gonna have like 1 to the power of x, right? A function like this. So 1 to the power of anything is, well, 1. So it will just be a straight line. It's really boring. So when x equal to 1, y is 1. When x equal to 2, y is 1. When x equal to 3, y is 1. So it's extremely boring. So we also say, well, b, the b term, cannot equal to 1 for that reason. Because if it does equal to 1, it would just be a constant number, like a straight line, horizontally at 1, which is extremely boring. So let's look at this type of function. In this case, let's say 2 to the power of x, and see what it looks like. So if we actually draw this graph, right? So to draw this graph, we're going to have some x value and some y value. And we're going to start with, let's say we start with a number that is like -1, right? So when x equals -1, what's y? So we put, so the y value should be 2 to the power of -1. That's what the x is, right? So you put the x into here, and then you get 2 to the power of -1. So what is 2 to the power of -1? So you have to remember, a negative exponent means reciprocal, and then the power. So the same power that goes in here is now in here. Well, that's 1/2, which is 0.5. So that gives us a point. When x equal to -1, right, that gives us a point. When x equal to -1, y equal to 0.5. So that's a point, and we're going to point it, dot it in there, in here on the graph. So when x equal to -1, y equal to 0.5, it's going to be right here. So hopefully you can see that dot right there. Okay, so that's going to be our first point. And then we're going to plot a few more. So the next one is when x equal to 0. And now, so x equal to 0, so we have 2 to the power of 0. Well, 2 to the power of anything to the power of 0 is 1. Okay, so anything to the power of 0 is 1. So this gives us a point of 0, 1. 0, 1, right? x 0, y equal to 1. And we keep going. So we say, okay, so what if x equal to 1? Well, 2 to the power of 1 equals to 2. Okay, so we have another point. So what about x equal to 2? Well, 2 to the power of 2 equals to 4. What if x equal to 3? Well, 2 to the power of 3 equals to 8. So we have like a whole bunch of points. So we have a point called 1, 2. We have another point called 2, 4. We have another point called 3, 8. And we're going to have them all plotted over here. So 1, 2, 2, 4, 3, 8. Now, look at the shape right now. This is the shape of an exponential function. Well, I mean, let's actually do one more. X equal to 4. X equal to 4, 2 to the power of 4. 2 to the power of 4 is 16. So you're going to get another number, another point, which is 416. So which is actually long enough to be shown in this graph. So look at how fast the graph is increasing, right? So we can use a different color of line to maybe put it all together. So look at this. So it's an exponential function looks something like this as a graph. So it increases very, very quickly. As x gets bigger, so the x value horizontally gets bigger, the y value goes up like an exploding. number. So exponential function, exploding. So that's, kind of how I remember it. Now, so as x gets bigger, the y value gets bigger. That's good. That's good and everything. But then there is something special about when x is small, as in when x is negative. When x is negative, you can get a number that is smaller and smaller and smaller, but they're not actually crossing to negative. They're just getting smaller and closer to zero. You can try it. Doesn't really matter what kind of negative x value you set. Even if you set x equal to, let's say, negative 10 or something, your y value is still positive because it will be 2 to the power of negative 10 in this case, right? X goes into the exponent. So what is 2 to the power of negative 10? Well, 2 to the power of negative 10 is, 1 over 2 to the power of 10. Now, 2 to the power of 10 is a big number. 1 over that big number is, pretty close to 0. But it's not negative though. It's just getting smaller and closer to 0, but it's never crossing to the negative side. So that's why we have this special feature on this graph we call these asymptotes. Now this particular one is a horizontal asymptote. So what is an asymptote? An asymptote is a line on the graph that your graph can approach to, but it can never cross. So we call it an asymptote. It's actually a horizontal asymptote. asymptote, asymptote. So now this asymptote is at the location of y equals 0. It's a horizontal line. Okay, so what is an asymptote? Asymptote is a line. So a line, it's a line. It could be vertical or horizontal. This one is horizontal. A line where your graph or your function, never reaches it, right? So it never reaches that point. So it's a line where your graph never reaches. So in this case, your graph can never reach y equal to 0. So y equal to 0 is called horizontal asymptote. Now, okay, so let's draw another one and make some observation. So let's go to the next page. So observation so far, exponential graph starts slowly. So it starts slow, but eventually increases very quickly. That's the first thing, right? Exponential function have something we just mentioned, horizontal asymptote. So horizontal asymptote, a line which the graph will get closer and closer to but never actually touch. Okay, now how about x-intercept? Okay, well, let's draw this next one and then actually check it out. So now this is also an exponential function, so we're also going to draw it the same way, which is having a list of x and y value, the easy way to do it. So let's do the first thing, which is let's say when x equal to -1, let's see what we get. So we get 3 to the power times 2 to the power of -1, which is the same thing as, remember, the power is that variable here. So when x equals -1, so we replace the x with the -1, and then this is 3 times, so remember that's reciprocal, which is 1 over 2, so that's 1.5, right? 1.5. So we have our first point. Our first point is -1, 1.5. Now let's draw like 2 more before we actually put it down. 0, right? Try 0. So 2 to the power of 0. Anything times 2 to the power of 0 is 1. So 2 to the power of 0, 2 to the power of 0 is 1. So 3 times 1, which is 3. So now we have another point, 0 and 3, and then we can plot that too. Let's try one more before we put it. So 3 times 2 to the power of 1. This one is easy, right? That's 6. That's 6 right there. So then we get 1, 6. That's another point. And we do, actually, I'm sorry, I'm kidding. Maybe one more. X equal to 2. X equal to 2. 3 times 2 to the power of 2. Now 2 to the power of 2 is 4. So it becomes 3 times 4, which is 12. I think we have enough points because the graph might actually go out of the picture if we continue. So now let's actually just graph these. So -1, 1.5, the first one right here, if you can see it, The second one, 0 and 3, right here. You can see it. And then the third one, 1 and 6, right here. You can see it. And then the last one is going to be 2 and 12. So again, it's a graph that grows up really, really fast. Now, also again, if you continue with this, you're going to see the graph eventually going to the 0, going to very close to where the horizontal lines are, but never actually causing it though. So I'm trying to link them together now. That's the shape of an exponential function. So exponential function always looks something like this. Okay, so it's approaching some kind of asymptote and then it's going up really, really quickly. Usually, if it's an exponential growth, that means it's getting bigger. And again, we also can see that horizontal line at y equals 0 that you are never supposed to touch. So let's answer all some of these questions over here. Right, these questions over here. Okay, so x-intercept. Now what is x-intercept? So you have a graph like this, right? That's the x-axis. That's a y-axis. That's your coordinate plane. Now sometimes you have a graph that's crossing over the x-axis. So then we call that x-intercept. But do we have that in here? The x-axis is where? Here, right? So this yellow highlighter thing, that's the x-axis. Can our graph actually cause it? No, right? That's actually one of the features of exponential function. You can't really cross that line. So therefore, x-intercept, the answer is no. No, we don't have any. So no x-intercept. Now, we do have only one y-intercept. So and that y-intercept, so same idea, right? So you have your y-axis, your x-axis. So this is your y-axis right here. So sometimes you see a graph crossing it. So that's called a y-intercept. So do we have a y-intercept? Yes, we do. We do in this case. So the y-intercept is actually this point right here. I am highlighting it in blue right now. That's your y-intercept. It's crossing y-axis at 3. Okay? So that's called a y-intercept. Now, let's do that.